Hello and welcome to Kelly and Cassandra's presentation of Chapter 12 in our textbook, Teaching and Learning with Technology in Science, Engineering, and Mathematics. Your two presenters today are Kelly Huddleston and Cassandra Amaya. Kelly teaches STEM and design classes at a private college prep school in Nashville, and she coaches her high school competitive robotics team. Cassandra works in IT at a mental health facility in New York. These are the topics we'll be covering in this presentation. After an introduction, we'll talk about the issues, challenges, and technology integration strategies for science, engineering, and math. We'll conclude with a short class activity that will involve coding a virtual robot. Introducing STEM. The learning outcomes, as noted in the textbook, include distinguishing three approaches to STEM integration for use in different learning contexts, explaining current issues and challenges for STEM integration, and selecting technology integration strategies to meet learning and instructional needs in STEM integration. All 7 of the EDDE standards for educators are covered in this presentation. Our authors state there is considerable concern in America today regarding students having equitable access, participation, and experience in STEM learning. Achievement gaps in STEM and mathematics are well documented, with particular recognition of a continued underrepresentation of female and minority STEM professionals. The graph on the left demonstrates the low ranking of the United States compared to other first world countries relating to mathematics achievement of 15-year-old students. The U.S. is the orange line toward the bottom, ranking 33rd of the 41 countries shown. Students from much of Europe and East Asia perform better than American students in math. The graph on the right highlights the gender, race and ethnicity, and disability status of the STEM workforce. Within the U.S., STEM fields continue to be dominated by white men with no disabilities. So what exactly is STEM integration instruction? There are 3 types of STEM integration relating to content, context, and tools or applications. STEM context integration is a way of teaching that merges learning from multiple STEM disciplines. The learning experience emphasizes one discipline while using contexts from other disciplines to create meaning and relevance to solve a problem. STEM content integration puts the learning emphasis on one discipline while using context from other disciplines to frame the lesson to create meaning, relevance, and/or motivation to solve a problem. STEM tool, or application integration, suggests that a tool or application of one discipline is used within the teaching of another discipline in order to help students learn the latter discipline's content. Now we'll address science instruction. I love this quote from the authors. The difference between science and engineering technology is that the purpose of science is to understand the natural world, whereas the purpose of engineering is to modify the world to meet human needs. Technologies are products of engineering design processes, just as scientific discoveries are products of scientific inquiry and argumentation. Our text addresses 4 main issues and challenges in science instruction. The first is holding to those science standards your school or district has adopted, 2 of which can include the framework for K-12 science education and the Next Generation Sciences Standards, or NGSS. Links to both are provided on the slide. The second issue addresses the need for our students to become scientifically literate. The third challenge relates specifically to elementary level science teachers because they are often licensed to teach multiple scientific areas. They lack a deep understanding of any one field. It's a case of jack of all trades, master of none. The fourth focuses on designing for ambitious teaching and inquiry, or AST, as well as the 5E instructional model. The AST and 5E instructional models meet the learning goals set forth in both the Framework for K-12 Science Education and NGSS. You can click on any of the underlined words on this slide to visit those websites for more information. This last slide for science instruction provides several technology integration resources for teachers that align with the AST and 5E instructional models. Links to many of them are included on this slide. Next, we'll head into engineering instruction. The three main by our authors include distinguishing the difference between science and engineering, holding steady in teaching the engineering design process, and teacher training. Learning the engineering design process is really at the heart of the discipline of engineering education. One of the major benefits of learning this process is that you can use it for virtually any problem in any discipline. Its usefulness extends far beyond just engineering. Regarding technology integration strategies in engineering instructions, there are four primary areas. First, engineers communicate their ideas and designs to themselves and others through notebooks, sketches, diagrams, schematics, reports, presentations, etc. Developing technical communication skills is crucial. Second, engineering students should be engaged through the use of makerspaces, innovation labs, fab labs, or whatever you want to call it. These spaces are often outfitted with 3D printers, laser cutters, wood shops, sewing machines, and centers for exploring coding and circuitry. Third, introducing students to robotics, coding, and simulations is another way to spur interest in engineering. Coding with physical robots can encourage understanding by helping students translate one type of learning into another, such as using math to figure out the path a robot needs to take to accomplish a task. And finally, teachers themselves should continually receive training in engineering principles through both virtual and hands-on activities. And last up, we have mathematics instruction. Math and technology have a unique relationship. Students have to be better prepared to use technology efficiently and fluently, both so they can learn mathematics better and apply what they learn in the workplace. This requires educators to reconsider what and how mathematics can be taught and learned. Technology provides many opportunities to build students' conceptual knowledge of mathematics, as well as to connect their learning to problems found around the world. Much like science and engineering, the major issues in mathematics instruction have to do with holding high standards, as well as implementing state standards and bringing research-based technology practices into the classroom. One method to address the standards challenge is to adopt a framework such as the Standards for Mathematical Practice, or SMP. Through the SMP, there are 8 standards, which you can see on this slide. Physical manipulatives, such as blocks, Legos, coins, or even candy pieces, can help students bridge the conceptual distance between concrete and abstract mathematical concepts. Research suggests that virtual manipulatives are just as effective, and in some cases more effective, as teaching tools for mathematics. Manipulatives provide several benefits to students, including helping them to focus on the mathematical task at hand, providing opportunities to express creative problem solving, linking representations with one another, demonstrating precise calculations, solutions, or representations, and motivating students to persevere. Resources to some of these links are provided on this slide. Handheld graphing calculators and graphing software allow students to graph equations as well as perform calculation functions in higher-end math and science problems. Research has shown that these tools can improve students' understanding of functions and graphs, as well as the interconnections among the symbolic, graphical, and numerical representation of problems. Regardless of how many mathematical facts, skills, or procedures students learn, the true value of mathematics is realized only when they can apply their knowledge to solve problems. Mathematics teachers must work to help our students develop data literacy and support mathematics-related communication. To wrap up the mathematics section, listed on the slide are several resources that offer skill building and practice activities for students as well as teacher training. Our sources are listed here. And now we will jump to our virtual robot coding activity. Click the link at the bottom of the left of the slide. This will open up a new browser tab. Welcome to VexCode VR. When you open the tab in your browser window, it probably looks like what I've got on my screen, and we are going to click the blue button that says Continue to Free. And come up to the top right corner and select Playground. Scroll all the way down, and the one we're going to use is called the Number Grid Map. This is the intro I do with all of my coding classes, but you can go as complex as you want. So with any program, using block code especially, we're going to come to the Events menu on the left, and you're going to click and drag in When Started. From there, we're going to come back up to the top under Drivetrain. Just to make things go faster, what I like this with is we're going to set the velocity and the turn velocity. Just click and drag them in. Start at 50%, but click and set them both to 100%. That just makes the testing process go faster. Now, the next thing I usually have them do is we are going to drive the robot to today's date. And right now I'm doing this on Sunday, April 21st, 2024. So the first thing we're going to do is have them go to the number 4 to represent April, and then navigate their way to the number 21 to represent today's date, and then over to 24 to represent the year. So computational thinking requires us to go one step at a time. So the first thing we need to do is have our robot turn right 90. Let's come test that and see if the robot does that much. And it did. So next we have to figure out how far forward it needs to drive. Each one of these squares is 200 millimeters by 200 millimeters. So to go from square 1 to square 2 would be driving forward 200 millimeters. To square 3, to square 4, you would just do some multiplication, or you could do some addition. But I'm going to pull in my drive forward, and let's try 600 millimeters. We're going to reset the robot, play, and there it goes. So now usually what I do with my students is we'll talk about different ways to get to the number 21. So for example, the robot could turn and go up to 24, and then over to 21. The robot could turn 180 degrees and go back to 1, and then up to 21. Or conversely, if you want to throw a little bit of pre-algebra, trigonometry in here, you could figure out the angle as the most efficient way to go from 4 to 21, to turn that degree, and then figure out how far forward you would need to go using Pythagorean's theorem. A squared plus b squared equals c squared. So that is one very simple virtual coding robot activity that can also incorporate some math. And once you get going, there are all sorts of other activities you can do. We can also pull in some physics to figure out rotational speeds and all manner of engineering. And that is our time today. Thank you for your attention. If you would like to get in touch with either Kelly or Cassandra, our emails are listed.